Hello, everyone. Good afternoon, everyone. This is our technical session 5 in SVR 2021. We have in this session 4 articles, 3 short papers, and 1 full paper. And our topics here are healthcare, assistive, and adaptive. So we are put the video of each study, and then we have time for some questions, 2 or 3 questions about for each article. So we ask you to put your questions in the chat of YouTube, and you will present the questions for the authors, okay? Good session for everyone. Let's start.
Hi, my name is Renan, and together with Márcio Pinho, I would like to present you our work called Virtual Reality in Radiology, a Systematic Mapping Study. Let's start by presenting our agenda for this presentation. First, we are going to introduce you to the context of our research. Later, we will detail the methodology we used. Then, we are going to present you the results and analyze them afterwards. Finally, we are going to review what we've just presented. Regarding the context of our research, radiology is a medical discipline in which images visualizing human bodies are examined for abnormalities. The interpretation of these images is considered a highly complex task since medical images are not self-explanatory. Here is a picture that depicts a typical radiological image. And to work with those images, radiologists make use of traditional desktops to diagnose. Doctors have to deal with the presence of external factors such as external lights and screen color saturation when diagnosing, which might interfere with the process. And here is a typical radiology reading room. With that context in mind, the objectives of this study are determine and characterize the state of the art on virtual reality in radiology, discover the uses, benefits, and main barriers of virtual reality in radiology, and identify gaps for future studies. To do so, we came up with 3 research questions, these being, how is virtual reality used in radiology? What are the benefits of using virtual reality in radiology? What are the challenges of using virtual reality in radiology? As for our general string, we created virtual reality or VR and radiology. And the databases we decided to explore were I3E, ACM, Engineer Village, Science Direct, Scopus, and PubMed. In order to filter out the amount of papers we would obtain from the electronic database we've just presented, we decided to only include papers from January of 2014 to July of 2021, papers accepted in journals, conferences, workshops, and symposia, and papers written in English. Here is a table summarizing the number of work we found on each database. In total, we've got 329 papers to apply our exclusion criteria. Speaking of which, our exclusion criteria were duplicated papers, literature only available in the form of abstracts and presentations, and publication not related to the field of study. And after applying our exclusion criteria, we ended up with 24 papers worth analyzing. And by reading all these papers, we were able to add 3 different categories for them. The first one is regarding the contribution of the paper. We realized they could be classified into 5 different ones, these being diagnostic imaging, medical education, patient care, interaction technique, and tool. The second one is regarding its research type, these being validation research, evaluation research, solution proposal, philosophical paper, opinion paper, experience paper, and overview paper. Finally, the third one is about their computer target, these being desktop, smartphone, head-mounted display, and Cave Automatic Virtual Environment, CAVE. As for the results of our systematic map, I highly suggest you to pause the video and take a look at Table 2, which depicts the classification of the papers regarding its publication year, research type, forum type, contribution, and computer target. From the Table 2 we've just presented, we can see that most papers and traditional desktops as their main research deployment target. Besides, still from the same table, we can also say that the categories with the highest number of studies throughout the years are diagnostic imaging, medical education, and patient care. And because we went through all the 24 selected papers, we were able to answer our research questions. The first research question is, how is virtual reality used in radiology? Well, it's been used in three main areas. Regarding the diagnostic imaging, it's been used to create virtual environments for radiology reading rooms and to visualize complex data sets. About medical training, it's been used to make preoperative decisions and provide surgical operation simulation. Finally, regarding patient care, it's being used to treat magnetic resonance imaging anxiety and educate patients regarding their treatment. Regarding the second research question, what are the benefits of using virtual reality in radiology? First, it improves diagnostic accuracy. Besides, it could also cut equipment and maintenance costs. In addition, it renders a comprehensive and intuitive visual representation of the data, even for non-specialists. Furthermore, it augments the possibility of grasping the complex morphology of anatomical structures. Moreover, it allows surgeons to take completely free perspectives on the anatomical structures. Lastly, it distracts patients from the unpleasant sensations of the scanning procedure. Lastly, the third research question, what are the challenges of using virtual reality in radiology? Well, the development of high quality content requires a degree of technical knowledge that is beyond what an average technology user possesses. In addition, many head-mounted displays are not suitable for radiology due to their magnetic components, which are strongly attracted by the MRI scanner magnets. Besides, there is also the physician's resistance to novel systems and technologies. Finally, the immersion in the virtual environment might increase the emotional gap between physicists and patients and potentially contributes to objectifying patients. Wrapping up this presentation, we will briefly revisit the highlights of this study. First, we performed a systematic literature study, and from 329 papers, 24 were considered relevant to the topic. Then, two possible gaps were found. The first one is about the exploration of other computer platforms when creating virtual reality solutions for radiology, such as smartphones and caves. And the second one is about the exploration of other areas of virtual reality in radiology, such as patient care and interaction techniques. And due to the 24 papers selected for this study, we presented insightful answers for our three research questions. Thank you for watching.
Very good, Renan. We have time for some questions. And while we wait for questions from YouTube, I have some questions for you, Renan. The first one is, you identified some gaps. It is very good. I think you conduct a very good systematic review. But in terms of applications, what do you think, what type of applications did you not find in your systematic review that you think that could be developed for VR developers? What kind?
I've noticed a bunch of solutions actually. They usually aim to help radiologists to give or to provide a diagnosis to images, and also for medical training. But the thing that I didn't find, and I highlighted that on my work, is that I couldn't find papers or work or applications aiming for mobile platforms such as smartphones or even caves. Maybe not only maybe, but that must be because mobile device has way less computational power compared to an ordinary desktop, and also cave is not so straightforward to develop solutions. So actually, I don't miss solutions. I miss the deployment target for those solutions. Those solutions, they exist and they're really great. I only miss the target, such as mobile devices.
Very good. This was another question. I don't know if you analyzed this kind of issue, but did you find any application that is applied in daily routine of clinicals or hospitals, or not? Only research?
Yeah, I'm afraid to tell you that I didn't find any work being currently used on a daily basis. And the reason for that, there are two reasons for that. The first one is that usually physicians, they kind of resist to novel technologies, And I understand that it's possible to understand them. They want the health safety for the patients first, and second, they kind of don't want to learn something new. If they already know something that pays them well and and that thing does the job, why will I learn something new? It must be proven to be way better than the thing that I already know. And second is usually innovation in that area really takes years to happen, mainly because of the safety. So patients need to be put in first place regarding the advance in science, let's say. So that's why we
Yeah,
can't
great.
find so easily to be applied on the market. And yeah, it's understandable. I would like to be treated on a thing that would give me the best results as a patient. As a scientist, of course, I would like to see novel things going on.
Great. I don't know if I am sure, but I think the main type of users that you find is medical radiologists. Is there applications for patients or workers, for example, or not?
Yes, there are because there are some machines. I mean, some patients they do have some claustrophobic. Some patients are claustrophobics, so it's nice for them to have an alternative when they're doing such exams because sometimes the machine creates a sound. I mean, the machine makes a sound that really disturbs them, and sometimes it's not an adult, sometimes it's a kid. So having some sort of virtual reality as a distractive tool, something to distract the patients from the exam. I've seen this being presented in many papers as a distraction technique.
Very good. We have a new question from Silas. How are the X-ray images visualized in this VR environment? Are they a 2D or two-dimensional image the user can manipulate, or a three-dimensional or 2.5D reconstruction
Yeah,
of the image?
yeah. Actually, both of options are correct. I've seen papers that really reconstructs the 3D image, of course, because you have many slices of the human body. So that's why that's possible. It's possible for you to reconstruct the body, and you can explore that body in a virtual environment. So you can go back and forth, turn around, and position the object in the way you feel like doing it. In the way you feel most comfortable with. But there are also some works. I mean, there are also some applications that only put many different, let's say, virtual monitors in front of you. So instead of you having, so you don't need to have real monitors in front of you because in a virtual environment you can have any amount of monitors if you like doing. So that's why sometimes so both options are correct. You can either reconstruct the 3D image, but also explore 2D image in many different number of monitors in the virtual environment.
Great. Did you finish the systematic review, or you intend to continue?
No, I've finished.
Okay, because I think there is two important issues that could be considered. The first one is about the quality criteria. I don't know if you defined some criterion of quality to evaluate the articles, if they deserve to enter or not in your review. This is an important topic in systematic reviews, I think. And the other one is related that Silas asked you about the resolution of the exams. Because, for example, if I project a VR system to train a radiologist to diagnose, for example, the resolution of the images is very important. And I think we don't have a resolution enough to diagnosis in our head-mounted display, for example. I don't know if you discuss something like this.
Yeah, two things. Yeah, I agree with you about the quality tag. I would say for the papers, it would be nice for me to have somehow rated them regarding their category. I mean, regarding their quality, it would be awesome. I agree with you. I didn't do that. And the second thing is an issue. Actually, the second thing about the resolution and the computational power for virtual reality, that's actually a problem regarding virtual reality. And that's also true. That's one of the problems of bringing radiology to virtual reality, because you're definitely going to lose some color accuracy and resolution because you're doing that, because the computer must be able to render things for you on the head mounted display. So that's why if you put the full resolution, the full colors, probably you would need to have a very powerful computer. So that's why sometimes people just lower the resolution, so you kind of lose information when you do that. But but we are in a phase where we are experimenting. We're trying to see if that solution in the future might be doable. So that's why we as researchers on that area, we understand that lowering the resolution just to see if that solution will be doable in the future is something acceptable right now. But that's one of the reasons it's not currently used on a daily basis on the market.
Okay, very nice paper and a very nice topic. It is a very interesting, I think, for our community. Congratulations, Renan.
Thank you very much.
Thank you. Would you like to to clap you, but we don't have the people here. But okay, let's see the second study. Thank you.
Leveraging simulation and virtual reality for a long-term care facility service robot during COVID-19. This work was presented at the Symposium on Virtual and Augmented Reality, and you can find the corresponding paper in the reference below. Today, Canada and many other countries are facing several challenges to ensure the well-being of seniors and people living with disabilities. For example, providing high-quality care to seniors and adults with developmental disabilities presents challenges associated with the high variability of conditions within that population and the limited resources available in the healthcare system. Canada also faces challenges related to its aging population. In 2017, seniors aged 65 and older accounted for 16.9% of the population, and this number is expected to grow to 24% by 2036. The census of 2016 also shows that 7.6% of seniors lived in collective dwellings, such as long-term care facilities. Regarding disabilities, 755,000 Canadians have some sort of cognitive disability. Around 3.9% of Canadians suffer from a learning disability, while 1.1% live with developmental disabilities. This sector of the population also suffers from inequality. It is estimated that 75% of working-age adults with an intellectual disability in Canada are unemployed and 70% live below the poverty line. On top of that, the world is facing several challenges in all spheres due to the COVID-19 pandemics. For technology development, some challenges are related to limited access to long-term care facilities, which was established to protect the residents. This hinders data collection and delays the delivery of emerging technologies. Emerging technologies, in combination with welfare, are addressing these challenges. For example, a study with 109 participants with developmental disabilities suggests that assistive technologies are beneficial to everyday functional activities such as leisure, social connectedness, and community engagement. The entertainment value of digital interactions employing game-based interventions such as serious games, exergames, and gamification can provide additional therapeutic benefits for improving well-being. Furthermore, a recent review on the usage of service robots to help elders, without cognitive impairment and with dementia, reveals that interactions help elders to achieve independence in basic daily activities and mobility by providing reassurance and reducing stress. That is why the Ether robot was created in a collaboration with the Developmental Disabilities Association, DDA. Ether is a socially assistive robot designed to help seniors and people living with developmental disabilities to achieve a higher degree of independence and to assist caregivers by alleviating the burden of care. The main use cases identified with DDA are safety inspection, where the robot searches for safety hazards or fallen people, and entertainment, where it performs cognitive stimulation activities. With the current access restrictions to DDA's facilities, we had to stop our in-site tests and our data collection and reinvent our processes. To overcome this challenge, we developed a simulator that employs virtual reality, or VR, to help us to test the robot. We created a virtual replica of a long-term care home from DDA for testing robot behaviors when navigating and interacting with a virtual avatar. Users can enter that environment to interact with the virtual robot by controlling avatars using a VR headset. The simulator also enables the generation of synthetic data for training machine learning models. It fosters the transfer of the knowledge built on the virtual environment, like the tuning of control parameters, to the real world. Our proposed system has a server computer, which runs the simulator written in Unity and communicates with the Oculus Quest 2 and the robot computer. The robot computer runs the robot operating system, or ROS, and the robot software stack that includes control, perception, and all other modules the robot needs. This architecture prevents CPU bottlenecks and ensures that the robot will have the same performance in the real world. This is a sample of the simulator, where you can see the setup with the robot and the avatar in the debug view. The user view shows what the user is seeing through the VR headset, and you can see that the user is able to control the avatar's head and upper limbs. Finally, the robot view shows the data ROS is receiving and displaying through its data visualization tool. Preliminary results show that the data from the real LiDAR, represented by the red dots in this image, is similar to that of the virtual LiDAR, represented by the blue dots. Both sensors detected the walls at equivalent distances, but some objects placed within the environment were detected with different distances. These differences were due to the misplacement of furniture within the virtual replica. The user could successfully control the avatar using the VR headset, and the robot sees the avatar's movement and obstacles through the RGBD camera and LiDAR. We also tested the EOLO object detection, which was able to detect the avatar and some objects in the scene. The integration of ROS with the Unity game engine allowed us to capture data suitable for simulating the robot's navigation and detecting surroundings, objects, and avatars in the long-term care home. An important limitation is that Unity's default extended reality framework supports only DirectX 11, whereas the Sensor SDK requires the ray tracing capabilities of DirectX 12. To overcome this, we adopted OpenXR. A byproduct of this project is the transfer of the virtual replica into virtual gathering spaces such as AltSpace VR or Hubs by Mozilla. These spaces have allowed us to connect with stakeholders to discuss various aspects of the project without requiring them to be co-located. We presented a virtual simulator that leverages robotics and VR for virtual navigation and human-robot interaction simulation. Our preliminary results indicate that the virtual sensor's data is suitable for virtually tunning ether, and that the VR simulator reduces the need to physically access the long-term care homes and enables remote collaborations between all stakeholders in the decision-making processes. Future work will focus on evaluating our current person detection and fall detection modules, and on generating synthetic data to train the machine learning models that implement our perception system. Thank you for watching this presentation to the end. You can contact us at ether@3srp.com and find more information at 3srp.com. We thank the financial support of MyTax, AgeWell, JDQ Systems Incorporated and the Developmental Disabilities Association.
Very nice, Silas. Very nice job. Congratulations. Silas, I have some questions for you. You put in your abstract that you intend to help senior people or people with some deficiency, I don't know, or problem, for example, with the robot. But I didn't understand if the control of the robot is immersive or not. But
I was muted.
Great.
So yeah, thanks for watching. Right now, this work is related to the virtual environment we build for tuning our real robot. So the robot is an actual robot that can navigate in the real space and interact with the residents and the staff. And the goal is to have this robot interact with residents to entertain them and like do some cognitive stimulative interactions like bingo or quiz games. And for the staff, the robot can talk to them and ask for do you need me to go around the home looking for hazards? And this hazard could be objects that are on the floor, fallen people, doors that are opened or windows that are opened. So this is the primary objective of the robot, like the physical robot. Now, the simulation is there to help us to continue the development considering the current lockdown restrictions, which doesn't allow us to go into the long-term care home and have the robot there to do real-world tests.
Very good, very good. We have a question from Victor. They said, great work, Silas. And do you use a co-design process with the senior citizens? How are they integrated into your design process?
So yes, we do have some co-design process, and this is done by, previously before the pandemics, we would do the development in-house, and then our team at JDQ Systems in Vancouver will take this robot to one of the DDA's long-term care homes. We would show the robot to residents and staff and have the robot do the interaction. And then we will talk to them and collect what were their insights on the robot, like what did they like, what they didn't like, what they saw as a potential area that we could explore or a potential problem. And then we would get like all those testimonies and create a report on that, and then work for a next iteration.
Great. You mentioned in your video that you plan, I think, an activity to transfer the knowledge from virtual to real environments. How do you think it's possible to measure it, to compare this transfer?
So right now we just finished the simulator, so we are looking into the actual metrics we are going to use. But what I expect to do is use the tuning of the parameters to make the robot, for example, improve the navigation. So we are sure that the robot can navigate from one point to the other in a safe speed and with good path. And we created a virtual twin of their long-term care home. So all the distance to objects, and we try as best as we could to place the furniture and other obstacles in the same place. So if the tuning in the simulation is correct, we would be able to see the same performance from the robot into the real world. So right now we are finishing up the small details and fixing some bugs to start doing this tuning on the robot. And once we are able to take the robot to the real scene, we can start doing this comparison. Like we run the simulation with a certain behavior, and then we run the same behavior on the real robot and compare what were the outputs.
Very good. I think it's a challenge because we have to consider the most real and virtual environments the most similar possible to eliminate some influences like this, the distances. I have to simulate the same distance in the virtual and the real. So it's not easy. Maybe you have to build a real environment very simple because it's not easy to simulate in the virtual world very complex words. I don't know, but I think it's a very good way to research.
I agree with you. And not only the environment has to be well simulated, we also have to do a good simulation for the sensors and the robot itself, because the robot has its mass, it has its own, I would say, dynamic and static interactions with the world. So we have to be sure that everything is as close as possible as the real version of not only the robot, but the whole system.
I think so. It's a very good challenge.
It is.
So thank you very much. Congratulations for your work. It's a very nice work. And let's thanks to Silas. Thank you, Silas.
Thank you.
Let's do the third article now.
Hi, I'm Franklin Bacias, and this work consists of the haptization of low-resolution image with a dynamic interaction to discern between different data. Tactiles are widely used in human-computer interaction applications, where they are used to transmit information as a means of communication, spatial awareness, and cessation of properties of objects through vibration signals. Physicalization is visualization of physical data, that is, they are artifacts whose geometry or material properties of the artifact encode data. This is designed to better support cognition, communication, learning, problem solving, and decision making. This work aims to use the representation of data by means of a set of vibrotactile actuators located on the back of the hand and interaction with the image to obtain a physically immersive perception of the data. We use 5 linear resonant actuators as vibration motors, and each area was placed at the distal interphalangeal joint of each finger of the back on the user's hands. To create a haptic stimuli, we use a pixel-based model to sample the vibration intensity that will be sent to each actuator according to the position of the mouse on the chart shown on the computer screen. Considering a low-resolution image, the large pixel pointed by the mouse defines the vibration of the actuator tree located on the middle finger. The horizontally neighboring large pixel defines the vibration of the actuator located on the respective neighboring fingers. We propose the use of a low-resolution haptic image. That is, each pixel has a signal x expressed as a function of time, where the amplitude of the waveform is the intensity parameter of the haptic signal. In this study, 3 haptic intensity labels of 25, 50, and 75% were used, with 100 being the maximum voltage delivered by the 5 voltage signal amplifier. The frequency of the waveform is the same in the 3 intensity label, being set at the maximum frequency sensible in the Janus subsystem of 250 Hz. To focus on investigating how a user perceives the difference between 2 vibrotactile signals while exploring a visualization, we create 2 squares side by side which convey each a haptic image. They are visually distinguished by the color blue and green and associated to data signals A and B respectively. Each square area represents a label of haptic intensity, and they are separated horizontally by a white streak of pixels without haptic simulation, in other words, amplitude equal to 0. In the experimental analysis, the factor analyzes what is the difference between each intensity in a pair, that is, 0, 25, and 50 percentile points. After interacting with the image, only one fixed question is presented to the subject for each task throughout the experiment. Does square B green have a greater vibration force than square A blue? With 2 possible answers, yes if B greater A, or no if B less A or B equals A. We created 4 haptic images overlaid by the squares. Each image contains 2 square areas of data A and B separated by a distance of 0, 2, 4, and 6 pixels, 35. With this, we wonder how a blank separation affects the comprehension of side-by-side comparison of haptic data. Also, how confident users feel with their guesses to tell the vibration signal apart as the intensity difference between them varies. Finally, we consider whether users can associate the vibration field as an extra dimension in the data being displayed. The average accuracy, average response times, and average mouse distance for each subject are recorded as dependent variables. According to Shapiro-Wilks test, the data was not normally distributed, so a no-parametric repeated measures test was performed with Friedman test, while post-hoc tests were performed with Wilcoxon signed rank tests, reporting the observed C-value, the number of observations, and the significance p-value. For more details, please see the paper. Post-hoc tests show that the accuracy of the intensity label is significantly higher than the previous one. No effect was found on the distance between A and B for the Friedman test. Post-hoc tests show that response time is significantly faster as intensity labels increase. No effect was found for the distance between A and B for the Friedman test. Once again, post-hoc tests show an effect of A-B intensity difference on average mouse distance, in which mouse distance decreases as the intensity label increases, and the mouse distance increases as the distance between A and B also increases. The maximum interaction points are in the horizontal center pixel of each square data area, where the same vibration is rendered in all the actuators. The heat map represents the metrics of the position of the pixel most explored during the task in relation to the difference in vibration intensity and distance between the A-B data. This map shows that the user seeks to fit a single render data value on all actuators and the hand at once, rather than having two values rendered simultaneously on different fingers of the same hand. After the experiment, subjects were asked 6 questions based on their experience and perception, being able to reply in 5-point Likert scale, related to vibration sensitivity in Q1, Q2, and Q3, related to self-confidence according to the distance between the data in Q4 and Q5, and related to the perception of a new dimension through vibration in Q6. With this, particularly in question Q4 and Q5, we can notice a slight tendency of users to find it easier to compare vibration when they are closer to each other. This also correlates to the mouse distance traveled, showing previous results which get greater as the A-B distance increases. Regarding question Q6, only 4 subjects seem to disagree with the vibration as a new perceived dimension premise. The significant difference for the response size is inversely proportional to the magnitude of the vibration difference. In the same way, the mouse distance traveled is proportional to the distance between the two data. The results accept H1 and confirms a behavior expected by the method used, that is working correctly by not having random results. The distance between both A and B data did not affect the user perception to discriminate the difference in vibration. They were reflected by not having significant difference between the clusters and most distant pair of distance, in addition to the previous Q4 and Q5 results. Regarding the results of question Q6, and considering that the accuracy in the trial had a minimum average percent of over 19, we have preliminary evidence in support of hypothesis H3, which pondered whether our approach effectively lets users comprehend vibration pattern as a new dimension to data being visualized. Thanks.
Thank you very much, Frankie. It is also a very nice article. And we have now a question from Silas, and you have other questions after. Great work for both Renan and Franklin. Silas congratulates Renan and Franklin. Franklin, are you considering creating a custom-made mouse that embeds the motors into the device, so the user doesn't have to wear a glove to feel the haptic feedback? Something similar to the current game controllers.
Okay, that's an interesting approach, but for this case, we use this type of custom made because the perception in the 5 fingers is useful to perceive each of interaction, each of signals of this vibration of this data. But with the results, is that other option to see in the future world? Because in the result related with the head map, we see the person of each user only search the vibration, the same vibration in whole of fingers. One question we have when starting this work, we think also maybe the people can understand the data or can difference each data when you had hollow vibration in different fingers. But the results is show different situation, like the person only search one signal in hollow fingers. So, but maybe on the future work we can consider this type of custom made.
Thank you, Franklin. Victor by YouTube also congrats you for the work, very good presentation. And he asks, can you tell more about the placement of the motors? What are the benefits of placing them on the back of the fingers? Very good question.
Okay, that was good. The placement was in the sensitive part of the fingers. That was interphalangeal joint. That is in the part joint in the or one of the more sensitive parts of the hand. That was considered as position because when we use signals or weak signal, no with great force or big force, the vibration. Also, we can consider the vibration. The user can perceive this vibration. So the placement in this part is it was searched in the art, in the style of art for this part. Maybe in other parts of the finger there are the good sensitivity in for the user. So this part was searching some articles with mentioned this part for a good perception and a good frequency. Also, we use the better frequency, I don't know if it's better, but the great frequency, the perception of the user can perceive what is 250 hertz. And also this combination is only thought about the perception of the user.
Okay, and Anderson asked, you used the mouse and a monitor display. In VR, with a head-mounted display, people could touch objects in midair. Do you think the results will change without a physical surface?
Oh, that is interesting question, because there are some approach of this part, but I have a theory. The theory is when you feel a texture, what happens when you feel a texture? You feel the relief of the texture, right? And what is this perception when does this happen when the shape of your finger change, right? And that is the cutaneous sense of the finger. Also, we use these motors, this motor with the vibration, change that shape of the skin. So maybe that can perceive like other surface or the objects. Maybe like I can see like a texture, because it's a little near of this approach. But with the perception of the change in the shape, the interaction with the mouse, augment this interaction with the data. But right, the VR and others approach, we consider for future work, and maybe like this topic in physical, in visualization, and other fields, right?
Great. So you said about visualization now, and in your paper, you present the motivation in the visualization context. And my question for you is, the experiment that you did for a while is about the efficiency of the system, but you didn't put together a visualization, for example, a 3D visualization with your system. Are you planning to do something like this to measure, for example, if your system, the haptic feedbacks, really can help it to understand the visualization?
Right, I can prove with the different results in the paper. Like heat map for understand the place in the user can understand this data, and the accuracy that we have in this paper. Is that also a topic we can consider, because all of the users had a good accuracy in whole. More exactly, the accuracy is for above the 90%, right? So all of the user can a good question, can a good result about the question in this task. But for the comparison between real object and virtual object, that needs other work, because we use the cutaneous sense, right, with vibration. But for a real object, for feel this shape, we use the kinesthetic sense. So it's other type of perception with the object. But right, we can search one bridge. We can join them. But that's a good idea for continue this work and for continue this goal to have this object perception in the virtual reality.
Okay, only a last comment. And when we see the Regina's talks today, she's talked to us about the accessibility. And I think your article, your work has a great potential, for example, to use it to augment, to contribute, to help blind people to see visualizations. So maybe you can think something about that. Okay.
Yeah, that's a good idea. Thank you very much.
Okay. So let's talk. Thank you to Franklin. Congratulations, Franklin. Thank you very much.
Bye.
Okay. So we will present the last paper in this session. Please.
Hello, I'm Julia from the Assistive Technologies Lab at Federal University of Uberlândia. First, an introduction. So, I'm Julia, and I have some experience building XR games for post-stroke rehabilitation, and I've noticed a lack of accessibility of this therapy to private patients and therapists. The main reason why this therapy wouldn't get to the end user is the cost problem. Because I would build something with an electronic sensor, for instance, an inertial sensor, that is a little bit expensive to some private patients. And also, for playing a 3D game, it is necessary to have a graphics card, which is a second processor on the machine, only to process graphics, and this also increases the cost a lot. So this makes the system a bit more inaccessible to the patients. My objective with this work was to keep the 3D tracking of the arm, keep the 3D graphics, but make something more cost accessible. So this is what I did. I used Unity, Blender, Free Music Archive, Vector, GIMP, OpenCV, and TreeIt tools. And I've used some algorithms of the OpenCV library, which are camera calibration to compensate for distortions of the camera. I used the color segmentation algorithm and the pose estimation algorithm. So let me explain the solution that I got in a video. Here is my system. It's called Free2Fly. So this is the interface. First of all, the user has to enter this camera calibration panel and calibrate the camera with this checkerboard pattern that is glued on a cardboard. And I am taking 4 photos, but at minimum 2 photos are necessary. Then I use these parameters to the camera image. Then, as you can see, I have styrofoam spheres attached to my shoulder and to my hand, and I go and calibrate their color, their size, and half of the length of my arm. And then, as you can see, I can achieve the elbow angle in real time in 3D. And I'm using only styrofoam balls, which can be any color. I also enter the configurations panel to put my email and have some performance options also. So then I make a small difficulty adjustment, and then the user can play. This game is on a beach. This is a Macau, and you have to move left and right with your hand, up and down with the flexion and extension of your elbow. So I'm capturing the angle of the elbow to move the character, and the goal is to capture these fruits on the scenario. So this is it. At the end of this session, I ask for the patient to draw a small pattern for me to make a little assessment of his motor coordination. And that's it. Then I generate a session report with some important parameters such as angle range, a score, and the images of the drawing tests through the week, and send this to the therapist via email so that he can monitor his patient remotely. And I also keep a database in the clouds with information such as demographics of the patients, the tests. So I've tested some factors that influence the accuracy, such as angle value and the sphere's coordinates, and the results. I noticed that the angle value is worse, is less precise at more obtuse angles. This is due to the Cortland formula, which is a sine wave, so it's the same graph. More precisely, I had an error of at least 5 degrees at 110 angle of the joint. Also, I noticed that the capture is more precise in the center of the camera, because I couldn't eliminate the sphere distortions very well, as you can see, with the OpenCV algorithm. This is a pilot test with an occupational therapist and a post-stroke volunteer. She really liked the game. So my conclusions: I was able to build an innovative motion capture in 3D using only a regular camera, which can be your smartphone camera. The game can be processed on a mobile device, which is intermediate, doesn't have to be a great mobile device. The user can manufacture the control device at home with craft materials, doesn't have to buy any electronic sensor. And the system has accuracy limitations for being so simple. As future work, I would like to improve the stability of the capture and the usability of the interface, test the correlation of the measurements of the game with standard scales that measure clinical progress, and make the software available on worldwide distribution platforms. That's it. Thank you very much.
Thank you very much, Julia. Congratulations. Good job. So we have a first question from Silas. Great presentation, Julia. Why did you decide on using colored balls rather than fiducial markers? Do you intend to use some tool like media pipe or similar to get the 3D pose detection from the camera image to simplify the calibration?
Thank you, Silas. This is a great question. Before developing this system, I made an extensive literature review. And one of the things I tested were fiducial markers. The OpenCV algorithm for fiducial markers, I found it to be very slow. I was able to achieve around 10 to 15 frames per second without the processing of the game. So it was really slow. And also there was the problem of the fiducial marker needing the camera to be very, because the fiducial marker algorithm, it's a detection algorithm rather than a tracking algorithm. So you need to be very still. In this game, the person will be moving the arm. So the pattern that is printed on the fiducial marker is going to be blurred due to the motion blur of the camera. So this is also a problem. The person has to move very, very slow for the fiducial marker algorithm to work, and it's processing heavy. And media pipe is a solution that is very recent. When I was developing this game about a year ago, media pipes didn't exist. And deep learning for smartphones were solutions that were really, really slow because deep learning requires a lot of calculations. But MediaPipe changed that. MediaPipe was released about 2 months ago, and it is deep learning for pose estimation, but really, really fast. And they provide a 3D estimation, okay? The 2D is great, I agree. I could replace the hand ball with MediaPipe for 2D tracking, for example, for drawing that star. But for 3D pose detection, I found MediaPipe to be a little bit imprecise. It wasn't very reliable because they use the 2D pose estimation to estimate the Z coordinates. They don't take into consideration the camera distortions, and I found the estimation to be a bit unreliable. But in the future, in the very near future, AI and MediaPipe and deep learning will replace this technology very near in the future.
Thank you, Julia. Also, Victor, congrats you. Great, Julia. Would it be possible to use the other objects as markers or only the colored spheres?
No, for this system, I had to use spheres because they are round. As you can see, you move the arm in an angle, and the sphere is the only object that maintains the radius. Regarding where you're looking, the sphere has the same diameter. So that's why it has to be a sphere. So this uses the sphere diameter to estimate the third dimension. That's why it has to be a sphere. It can't be a cube, for example, because when you look at the cube sideways, it has a larger diameter. So it can't be a cube. It can be there's another shape that it's called isododecahedron that can also be used. But a sphere is simple, and the sphere can be any color. I made them from styrofoam, which is isopor, and just painted it, and you just glue them with regular tape, and you can play the game.
Okay. Only a last question to finish. You put in your video that you have limitations in relation to accuracy. Is that related to camera resolution?
Yes, but the cameras, if it's HD or full HD, is already enough. The biggest challenges I had was the problem that the spheres have. For me to find the third coordinate, I had to use the chord length formula. And that formula is a sine wave. So it isn't a straight function, which means at more obtuse angles,
Okay.
I got a lower accuracy, but much lower. And I cannot solve that. And another problem I had was the distortion, the radial distortion of the camera around the, you have a lot of distortions in this radius. Also, this I couldn't eliminate for spheres. And for instance, if you open the window of the environment, you will have a lot of illumination variation. So you have to be in a closed window environment with artificial lighting. And that's it. But it's very usable for now, while deep learning doesn't replace it.
Great. If you have problems, you have opportunities for research, new research. So it's good. It's not bad to have problems and limitations.
Yes.
Yeah. So thank you very much. It's a very nice job, Julia. Thank you. Let's thank
Thank you so
Julia.
much.
So this was our last article in this session. I think it was a very productive and participative session. Thank you everyone for participating and sending questions for our articles. And congratulations for all the authors of the articles that I think they were very nice in this session. Thank you. We have now a session at, I don't know if Dani or Victor can confirm me, at 6 p.m. It's okay to have a panel, isn't it? Yeah.
Yes.
So let's together to the panel at 6 p.m. Bye-bye. Thank you.
Bye-bye. Thank you, Fatima. Bye-bye.